right, let's talk graphing logarithmic functions. Unfortunately, unlike with previous functions, there's no like quick way to actually graph them. And so we're just going to have to use coordinate mapping, which you may have seen in grade 11 anyways, so hopefully you're familiar with it. And if not, it's not a difficult concept to process. The trickier bit will just be using the logs. Essentially what we do with coordinate mapping is we start with a few values from our parent functions. Then we apply the necessary reflection, shifts, reflection, stretches, and then shifts in order to figure out sort of where our function lands at the end of the day. And then we're going to use those points to plot on a graph so that we have an idea of what our transformed function looks like. In the first one here, in both of them, I'm going to graph the original function, the parent function, and then I'll also graph the transformed function so we can take a look at what it looks like. Now, the tricky part here is knowing where we're starting off at with log functions. What are some of those sort of key values from our parent function? Remember that log, so in this case, we've got a log base 2. So what that's saying is I have log base 2 of x is equal to y. Another way of saying this is 2 to the power of y will be equal to x. For example, if my y is 1, 2 to the power of 1 is what? The answer is 2. Okay. If we were to write that as a log question, it would be log base 2 of 2 is equal to what? 2 to the power of what gives me 2? That's the question we're asking here. Okay? If f of x or y is 2, my x is going to be 2 to the power of 2, which is 4. If my y is 3, then I'll have 2 to the power of 3, which is 8. And if y is 4, I'll have 2 to the power of 4, which is 16. And you could keep going and keep generating this way. Notice how we're going up by 1 in the f of x column, but when we're moving up the x's, we're actually doubling it every single time. And that matches with the fact that we have a base 2 in our logarithmic function. That's where that comes from. Okay, so anyways, these are our original points, our original coordinates of our function. Let's actually sketch this out so we can see what it's going to look like. I'm just going to plot these on the graph here. 4 up to 2, 8 up to 3, and then 16 up to 4. And then we would connect the dots with a nice smooth curve. And of course it has a vertical asymptote at 0 that we're going to get close to and never touch. So that's our parent function. This is our f of x is log base 2 of x. Now let's go about doing our transformations. The first transformation we're doing is a reflection. This is being reflected vertically. It's being reflected across the x-axis, which means that our y values, our f of x values, are the ones that are being affected. They're going to become negative. Our x values are going to remain the same, but the y values will become negative instead. That's all coming from right there. Okay? The next things that we have to look at is our stretches. What stretches do we have here? We have a vertical stretch by a factor of 3. So we need to multiply all of our y values by 3. X values once again remain the same. And now I'm going to reference my newest y values when I'm multiplying by 3. So negative 1 times 3 is negative 3. Negative 2 times 3 is negative 6. Negative 3 times 3 is negative 9, and negative 4 times 3 is negative 12. So all of those numbers have now been multiplied by that a value to reflect our vertical stretch. And then last but not least, we have our shifts. The only shift that's present here is this plus 4, which we know is a shift to the left by 4. So what I need to do is I need to I need to take my x value and I need to subtract by 4. So in this case, our y values aren't changed from the last time we updated them, but the x values I'm going to take away 4. 2 take away 4 is negative 2. 4 take away 4 is 0. 8 take away 4 is 4. And 16 take away 4 is 12. So this right here, I'm just going to highlight these so we remember that they match. But this right here are the coordinates of our transform function. And so these are the ones that we're going to plot to show the transformation on our graph. Okay, so I'm going to plot negative 2, negative 3, 0, negative 6. You know what, I'll do this in a different color. I'll do it in light blue. Negative 2, negative 3, 0, negative 6, 4, negative 9, and then 12 down to negative 12. Okay, we did have a vertical asymptote previously, which was at 0, and we've now shifted our entire function to the left. So I know that there's a vertical asymptote coming, located at negative 4. Okay, so I will give this a good sketch, try to keep it as smooth as possible. And add some arrows to the end. Okay, this is our transform function. This is our f of x is negative 3 log base 2 of x plus 4. Okay, we'll do a second one now, just so we can see everything that's happening. Let's start by filling in our table of values. Just like last time, I'm going to use y values. I'm going to put those in first. And remember how we generated it? We used the base of our log, so in this case was 5. And we said, well, what's 5 to the power of the y value? So in this case, 5 to the 1 is 5. 5 to the 2 is 25. And 5 to the 3 is 125. So I hope that you can appreciate why we're only doing 3 values here, because that's a lot to sketch. I'm going to add these onto my graph. At 5, 1, I'm working here, 25, 2, and then 125 and 3 with a vertical asymptote on the y-axis. And I'm going to try and sketch this to look like a nice smooth curve as best as I can. And it's going to take a really tight turn going down there. Did my best. Okay, now let's start doing things. First of all, reflections. There's no reflections, so our points remain the same. 5, 1, 25, 2, and then 125, and then 3. Stretches. There is one stretch. It is a vertical stretch by a factor of 1 over 2. So I actually need to be dividing everything by 2 or multiplying by a half. I'm going to go multiply by 1 over 2. And this is, again, vertical only, so my x values remain the same. And these I'm going to cut in half. So 1 is going to go down to 1 over 2. 2 is going to go down to 1. And 3 is going to go down to 3 over 2. So these are what has been affected following our vertical compression there. And then last but not least, we have two shifts that we have to consider. The first one is a shift to the right by 5. And then we also have a shift up by 10. To the right by 5 means I need to add 5 to my x value. And up by 10 means I need to add 10 to my y value. So both of the values are going to be changed in one go. Let's do x's first. I add 5. 5 plus 5 is 10. 25 plus 5 is 30. 125 plus 5 is 130. Now let's add 10 to all of our values. Half plus 10 is 10 and a half. 1 plus 10 is 11. 1 and a half plus 10 is 11 and a half. We can now go ahead and sketch our transformed function from our transform points. I will do that again in light blue. Our vertical asymptote has shifted 5 to the right, so I'm going to start by adding that in. And now I'm going to plot my points. I have at 10, and 10 and a half, about there, 30, and, we can go higher. 10 and a half is here, 30 is at 11, right, that's 30, yep. And then 130 all the way over here is at 11 and a half. So this dot. Woof. It's going to look the same, but I promise this is a transformed function. The vertical shift is obviously the one that we can see the best. Let's go ahead and try and add, that's going down too quickly. Try and make this look like a logarithmic function to the best of our ability. This is our transform function. F of x is 1 over 2 log base 5, x minus 5 plus 10. Okay, pretty straightforward, just takes a little bit of getting used to in terms of transforming the points if you're not. Otherwise, happy sketching.